So the output of this of the whole circuit is to get a pulse, which is a very short bit at every 0 crossings. This is fed to the microcontroller, which further performs the next step. Next is the timing diagram. As you can see, we have a rectified voltage from which we get down to these sharp signals. This is fed to the microcontroller, and this signals the microcontroller to generate a pulse width modulated signal based on, and the width of that signal is based on the frequency that's coming in to the microcontroller. So at this point of time, when we had the circuits, we tried to test it with a pulse generator, and we found out at the first test, the lights were still flickering. When we further went down, we found out that the real thing to control the intensity of the lights depends upon the timing. What I mean by that is, when you have the first trigger here and a pulse is generated, the pulse needs to be stopped right before the next 0 crossing. It cannot go beyond the next 0 crossing, because if we do so, then as we made you show in the triac here, if the pulse exceeds the next 0 crossing, the triac here will automatically shut it off once it detects the next 0 crossing. So no matter if you have a longer pulse, the lights will still flicker. So the key lies in the timing and the width of the pulse that's being generated. So the pulse generated by the microcontroller has to lie in between the two 0 crossing detected signals, and then we can play with the bits there. Next, I have some pictures which we used when we tested it. The blue thing which you can see here is actually an inverted form of the 0 crossing output, and the yellow one is the pulse that is produced, and it's a very small pulse, so the bulb is barely on, and the other ones here it's a little blurry, and this is like 50% on, and this is fully on. The fully on means the pulse is 8.3 milliseconds, which is the time between the two 0 crossings. That's the maximum you can get. So at this point of time, we have all the circuits ready, and we could actually control the intensity of the lights based on the pulse being supplied in, which is the thing in that box. The next part of the project was to integrate the circuits present with the microcontroller, and which was supposed to be done by a third member in our team, which is not here right now. And and we were assured throughout the semester that it could be done. At the end of the semester, we found out that our member was very ill and she could not deliver the stuff she had to do. So we could not perform the microcontroller part on our project. But for the theoretical part of it, at the very end of the semester when we found this, I have a new topology which we can use, in which, as you can see, I have replaced the microcontroller with a filter design circuit. Due to lack of time, we were not able to test it fully and make the thing work, but this is just on a theoretical basis. The filter design circuit looks something like this. On the top we have the filters, which is a 4-pole Chef filters, which have a high Q, so we have a high speed. They are fed to a full wave rectifier. The output that we get from the rectifier is actually the mode of sinusoidal waves, so we have a DC component and we have some AC harmonics. So it's fed to an integrator here, which removes the AC components and gives out a pure DC. It's then inverted and fed to a LM5FX timer chip, which basically performs the pulse width, which generates the pulse width modulation signal and it is triggered by the zero crossing trigger. So, and basically this needs to go to the light limit circuit to actually tint the lights. So, as I told you, we cannot really test it because of the lack of time, but it's just for illustrative purpose. This is the timing diagram. You can see from the AC we get to rectified, and this is the low frequency, this is the high frequency, and this is the DC output that we get. This is inverted, and based on the average DC voltage given, a pulse width modulation signal is generated. What we learned in the project is to actually build the circuits on hardware, allow signal processing, and lessons learned: don't blind trust. Always have a plan. Always have a backup plan. And special thanks to Professor Yang for his generous advice.